Okay, thank you for having me. Today I'm going to talk about connection between QCD, chirality, and some condensed matter physics consisting of topological insulators. Interested in not just in the connection between how you can use these topological insulators to do computations in lattice QCD, but also learn something about what the theory of QCD might look like if we had a theory of everything, which was a UV completion, and also suggest how this technology could help us understand how to regulate chiral gauge theories like the standard model. So perhaps one of the most fertile theories of the 20th century was superconductivity, and it taught us an enormous amount of quantum field theory, namely that the vacuum doesn't have to be simple, and that if the vacuum is complicated, all sorts of interesting phenomena can be explained. So it gave us chiral symmetry breaking. It gave us the Higgs mechanism. It gave us confinement and the dual Meissner effect. And it gave us topological defects in the form of strings. The basic message, though, was that the vacuum is complicated. And so this was such an important turning point for particle physics, which was sort of stuck with the successes of QED, but also the limitations of QED. And so it's natural to ask whether we can turn to condensed matter physics again and get more insight, because after all, they have the advantage of being able to create many different universes in their laboratory and poking at them, which we cannot do. So in the past few decades, what's really dominated the conversation in condensed matter theory has been topological materials. And so the question is whether these can tell us anything new that is useful for our studies of particle physics. So the first thing is that in translating some of the condensed matter physics to quantum field theory, you find that basically any type of massive fermion theory, free theory, has some analog to a topological insulator or superconductor. While almost any theory of massless fermions can be interpreted as the edge theory of a topological insulator. So these are not weird, exotic phenomena that you'd have to really add some bells and whistles to an ordinary quantum field theory in order to see the effects. But the effects are not the sort of things we normally look for. So some of the physics is a little bit hidden from the way we usually think about quantum field theories. The common thread between the condensed matter systems and the particle theory systems are anomalies. And it's, I think, key for understanding chirality and lattice QCD at least. But also, as I mentioned, there's some technology there that might be useful for providing a regulator for the standard model. So in the tenor of this conference, where people are giving a lot of personal references, I'm going to start off by just saying how I got into it. And interestingly enough, it started with a conversation with David back in 1981. I'd gotten into graduate school at Princeton and Harvard and MIT. MIT told me I'd have to pay my way, so that was off the list. Princeton was very attractive. I went there, and a secretary ushered me into the office of David, who was talking physics with Kurt at the time. And I saw their faces fall as I stepped in, because it meant they're going to have to stop talking physics for a few minutes. There's this short story by Ray Bradbury where the 350th Amendment to the US Constitution is that everybody has to be equal. And so strong people are weighted down with chains, and beautiful people have to wear ugly masks, and smart people have little radio transmitters embedded in their ear, which sends off a shrill whistle every time they have a good idea. And so I was the whistle for David at that moment. He had to stop doing physics, but he was gracious and sat me down and told me what he was thinking about. And I understood virtually none of it, since I was an undergraduate at the time, but he told me he was thinking about chirality on lattice QCD, and it stuck in my mind that I should learn something about chirality and lattice QCD. So that's stayed with me for all my life, actually. So the second big influence was a paper by Kaplan and Harvey in 1984. This was written in response to a very mathematical paper by Bruno Zimino, where he compared anomalies in different dimensions and showed how they are related. And it was all in terms of differential forms, and it was very formal. And Kaplan and Harvey wanted to have a working physical model that showed the physics that Bruno had discovered. And so they wrote this paper called Anomalies in Fermion Zero Modes on Strings and Domain Walls. And it's beautifully simple. They just said, suppose we have a system with a domain wall or a vortex, and we look at the Dirac equation, the presence of this. Well, it was known from earlier work by Jakiv, who among the people who should have been here, he was one, who considered with Rebbe what happens when you just solve the Dirac equation in the presence of a mass that has a domain wall structure. It's an incredibly simple problem. You could give this to somebody in a beginning calculus class. So what you find is that the Dirac equation has a solution of a, let's see if I can use this. The solution, this is confusing. It's exponentially confined to the domain wall. It's a particle that moves at the speed of light along the defect, and it only occurs with one chirality. The other chirality solution that you can write down is not normalizable, and so you throw it out. So the picture then is you have this, in this 2 plus 1 goes to 1 plus 1 dimension picture, you have a bulk which is full of massive states. You then have a defect where there's a massless fermion that travels along at the speed of light, and it only travels in one direction. So this is very peculiar. You might say, well, this violates parity or something, but that's okay, because in odd spacetime dimensions, the fermion mass violates parity and violates time reversal. So the theory has no parity. And it's sort of remarkable that there is a subsystem that does have a chirality to it. And you might sense that, well, chirality has to do with an epsilon tensor, because that's what tells what's a right from a left hand. And epsilon tensors always have to do with topology, because whenever you integrate an epsilon tensor over space, the 1 over the square root of the determinant metric under the epsilon tensor cancels the 1 in the measure, and you always are coordinate invariant. So there's topology hiding here somewhere, but it's not really obvious what it is. And at the time, it wasn't recognized to be topology, that there was any topology hiding behind there. But there is, which is interesting. It's going to be a part of the talk, a main part of the talk. So Kaplan and Harvey addressed the following issue, which is that it's known that a single chiral fermion in 1 plus 1 dimensions has a gauge anomaly. You turn on the electric field in the direction of the that the fermion is moving. And what happens then, of course, is that these states just sort of march up out of the Dirac sea, and the Dirac sea serves as an infinite source or sink for the fermions. You find that just using simple E&M, that the change in momentum is proportional to the electric field and the time it's applied, and therefore in a box that changes the number of particles in the box. And you get a very simple derivation of the anomaly. It's sort of a textbook example. Electric charge is violated. It's a sick theory, because you can't gauge a theory where charge is violated. And it relies on Hilbert's hotel, the infinite, the ability for the vacuum to constantly supply one more electron without ever becoming emptied. This also occurs, a similar model can be written out for 3 plus 1 dimensions, but not in 2 plus 1. 2 plus 1 electric charge is always conserved. So the question then is, if you've embedded this theory with non-conserved charge inside this bigger, higher dimension theory that has a conserved charge, how do the charges appear on the edge there? And it seems like this is sort of a conundrum, because you can apply electric fields of arbitrarily low frequency with very little energy in the system. And all of the fermions off of the domain wall have a big, heavy mass. They're gapped. So you don't have enough energy to create an excitation. Well, so Kaplan-Harvey's resolution is that when you integrate out the heavy fermions in the bulk, it gives rise to a Chern-Simons term. So the thing that's important about this calculation is that the coefficient of the Chern-Simons term has to know about the bulk fermion mass, because that's the source of the time violation and the parity violation. On the other hand, by dimensions, it can't depend on the mass. So the resolution is that what the Feynman graph gives you is just m over the absolute value of m. So the important thing is that heavy states do not decouple. It doesn't matter how big the gap is in the bulk, this thing is always generated. And furthermore, if you put in a domain wall profile, finessing the complicated physics right near the domain wall, you find this looks like a step function. So what Kaplan and Harvey showed is that if you differentiate this with respect to the gauge field to get the current, you find that there's a current that comes in through the bulk, and that because of the step function and its coefficient, it has a non-zero divergence, and that the divergence exactly accounts for the growth of charge at the defect. So this is how the Chern-Simons term in 2 plus 1 was related to the anomaly in 1 plus 1, which is part of the descent equations that Zumino had written down. So the picture they have then is quite simple. You turn on your electric field, the charge starts growing along the defect, and meanwhile it's just flowing in from both sides in through the bulk. So in the late 80s, I started thinking about whether this effect could be used to maintain chiral symmetry in QCD, because the salient feature of the model is that the overall model in 2 plus 1 has no chiral symmetry at all. There's no way you can define chiral symmetry in 3 dimensions, yet it has a chiral fermion sitting at the edge. And that seems useful because there's a problem with chiral symmetry on the lattice. I started talking to I mentioned this idea in the late 80s to some lattice practitioners, and they said, no way, no way. It's hard enough doing QCD in 4 dimensions, we're not doing 5. This is at a time when my desktop computer had 4 megabytes of RAM, which is barely enough for one photograph. And the extra dimension seemed like a way too big a price to pay for some, perhaps, solution to avoid fine-tuning to get chiral fermions. So my interest in lattice is not so much for computing things. I'm one of the few people who go to lattice conferences who've never done a lattice calculation. I'm interested in the fact that the way we think about quantum field theory has really changed if we think about the lattice. That's what Wilson did. So I was very surprised. I heard Pierre Ramond describing once going to Gainesville and talking to Dirac toward the end of his life and finding out that Dirac was extremely, not despairing is too strong a word, but he was very negative about his accomplishments in physics because he said there are all these infinities that were never resolved. That's really astonishing to me that Dirac could think that he had not accomplished much. He was at the beginning of what the demographers call the greatest generation. At the other end of the greatest generation was Feynman, who was quite happy to sweep the nasty stuff under the rug, put it in things that we can't observe, and say, let's just keep the finite bits and look at predictions for real observables, and there's no problem. Wilson came along and had a very pragmatic approach. He just says, I want to put this theory on a computer. How do I do that? And in trying to really put it on a computer, where you can't hide anything, you really are forced to rethink how to deal with quantum field theory. And so he really transformed how we think about quantum field theory in general by this question. So the issue that I was interested in was, how do you put chiral fermions in the lattice? And there was this Nielsen-Inomia theorem. If you start with an action, Euclidean action for a free fermion with some operator, which I've written in momentum space, they put out there are 4 things you would like to have. The first one is that D is periodic and analytic in momentum. That means that in coordinate space it's a local function. You'd like it to look like the Dirac fermion in the continuum limit as momentum goes to 0 compared to the lattice spacing, A. You want it to be invertible everywhere except for at p equals 0. That means that there's only one flavor, no doubling. And the last one is that there's some matrix that anti-commutes with D, which is going to be your gamma 5. That's your chirality. And their theorem was that you can only achieve 3 out of these 4. You can never have all 4. In particular, the one that is usually dispensed with is chiral symmetry, because it looks like the least dramatic one to eliminate. So when Wilson wrote down his theory of what are called Wilson fermions, he put down a Dirac term, he put down a mass, which violated chiral symmetry. He put down what's called the Wilson term, which is just a Laplacian, has the same chiral properties as a mass term. And then he said, let's take those 2 terms that violate chiral symmetry and tune them off each other to get a massless pion on the continuum limit. So global chiral symmetry becomes unnatural. The fine-tuning is analogous to the fine-tuning of the Higgs mass in the standard model. But furthermore, gauge chirality impossible in this model, so you could never do, for example, the standard model. So Nielsen and Ninomiya, there are all sorts of fancy theorems to prove it, but for me, it always came down to anomalies, which is that we know we have to come up with a chiral symmetry in the continuum, which is exact except for it has an anomaly, so it's not exact. So how do you do that on a lattice? In the continuum, you do it with the Hilbert hotel, but you can't do that on a lattice because you start off by having a finite Hilbert space. So if you take an electron from somewhere, you're going to have an absence of electron where you took it from. So, and then what Wilson fermions do, they say, okay, the anomaly breaks chiral symmetry. We'll just break it completely, and then we'll fine tune. But the fine tuning is not just for the pion mass. The fine tuning is everywhere you've got operators that have chiral properties. If you've got a bunch of weak interaction operators that don't mix in the continuum because they have different chiral properties, they start mixing on the lattice. So everything has to be fine tuned, and it's all power law in the lattice spacing. So my question then was, could lattice QCD, is it possible to have a lattice symmetry that keeps the good properties of chiral symmetry, namely no multiplicative no additive master normalization, but still has the anomaly? And the answer seemed to be to add an extra dimension. So the idea was just basically take the Callan-Harvey picture, put it on a finite lattice. And I first did it with naive fermions, and I found that instead of having 2 to the 4th fermions, I now had 2 to the 5th fermions. So the doubling problem just got worse. So, but then I realized that, the whole point was you don't care about chiral symmetry breaking in the bulk anymore. So throw in a Wilson term, and lo and behold, all of the doublers went away. So the idea then was you have a Wilson fermion. My original formulation had a domain wall in this mass parameter, but in fact, you can also just do it on a finite system with an edge with a constant mass. So you find massless edge states, you find Chern-Simons currents in the bulk without doublers, and the result is a tool for studying QCD with light quarks that doesn't have additive master normalization, but it does account for the anomaly. So I did the calculation for the easy case of m over r equals 1, where the difference equations become very simple to solve. And I suggested to my student Martin Schmaltz and postdoc Carl Janssen to just generalize it for different m over r. And they found something remarkably odd, which is that the number of edge states jumped abruptly at critical values of m over r of 0, 2, 4, and 6. So this is a sort of a panel of pictures of the 1 plus 1 dimensional Brouillard zone. So here I'm going from 3 to 2, from 2 plus 1 to 1 plus 1 dimensions. And each of these squares is a plot of the momentum in the x and t direction, namely along the 1 plus 1 dimensional defect. And the momenta go from minus pi to plus pi in lattice units. And I would do it for different values of m over r, ranging from 0, working my way down all the way up to 6. And in these pictures, where there's a white area, that's where you have chiral fermions on the edge, and in the black area, you don't. So it's sort of weird. You can have particles moving along the defect at the speed of light up to a critical speed, and then all of a sudden, poof, they're gone. There are no more chiral fermions. You can't get a higher momentum. And the way to understand that's very simple. You've got a mass term with a domain wall in it, and you've got a Wilson term, which is translationally invariant, which looks like a momentum-dependent mass. And as you go faster and faster, the Wilson term raises the domain wall until it's positive on both sides, and all of a sudden what's happened is your mode has become delocalized. It's paired up with the other mode on the other wall and gotten gapped. And in the limit where the walls are infinitely far apart, this transition is non-analytic, and that's the sharp boundary between the white and the black zones. So chiral fermions where it's white, no chiral fermions where it's black. And then the other thing is that where are the poles in the propagator? Well, in the top row of panels where the red dot is, you have a single fermion, and it turns out it's right-handed. However, when you go past a critical value, that mode is gone. There's no mode at p equals 0. Instead, you have two modes, one at pi 0 and 0 pi, and they're both right, and they're both left-handed. And then you continue raising m over r, and you end up with just one mode over here at momentum pi pi. That looks like a continuum mode also, but it's right-handed again. And then when you increase m over r too large, you don't get any surface modes. An animation of this, it's may or may not be illuminating. Over here, I've got a little dial which shows I'm changing m over r through different values from below 6 to above 6. And here I'm showing the same panels now as a movie, so you can see how the areas where there are chiral modes shrink and expand. Another way of looking at the same thing, this is in a one-dimensional version. I'm looking at the entire spectrum of the theory. So most of the states you see are the heavy bulk states away from the defect. Now as I change m over r, the spectrum changes, and when you see an x crossing either at p equals 0 or p equals pi, that corresponds to a massless continuum mode. And notice that they can come and go, but in order to come and go, all of the gap has to close in the bulk states. So that's the statement that to get rid of these modes, you have to somehow reduce the mass in the bulk so that the mode can actually spread out and get off the wall. So, but this caused a mental problem here, which was that, okay, if the number of edge states is changing abruptly, that means the Chern-Simons current has to change abruptly as a function of m over r, at integer values of m over r, twice integer. But how in the world can a Feynman diagram do that, right? You're just calculating a one-loop Feynman diagram to get the Chern-Simons term. I've never seen a Feynman diagram that gave me integers that were insensitive to the parameters in the Lagrangian, except for at critical values when it jumps. Well, it turns out there's hidden topology there. So again, topology on a lattice, how's that possible? You know, normally you think that one of the prerequisites for topology is a nice, continuous, smooth manifold. Well, so I was overwhelmed at the idea of having to calculate this using lattice propagators and lattice vertices. So to postpone the pain as long as possible, we wrote down an abstract propagator there with the right Dirac structure without specifying all the sines and cosines you have to put in there for a lattice propagator. So the inverse propagator is just some function of p times the unit matrix plus some functions times the gamma matrices. Then for the vertex, use the Ward identity that tells you that the photon coupling is proportional to the derivative of the inverse propagator with respect to momentum. And then you string them together in this diagram, and you pull out just the piece that contributes to the Chern-Simons term. That requires pulling out 1 power of momentum if you're in 2 plus 1 dimensions, and putting in an epsilon tensor. And when the dust settles, the diagram you have to compute looks like this combination of propagators where those derivatives are with respect to momentum, and they're contracted with an epsilon tensor. And so you immediately see that this looks like a topological winding number calculation. In particular, you find that you don't depend on the whole propagator. You just depend on this, this unit vector, momentum-dependent unit vector, which is constructed from the A and B functions I put in the, oops, sorry. Yeah, sorry. These A and B functions that I put in the inverse propagator are what determine which way it points. So you see this n of p is a mapping from momentum space, which is a torus on the lattice, to some sort of Dirac spin space. And we're calculating the winding number of that map. So momentum space is the torus, and 2 plus 1 dimensions is a 3 torus, Euclidean 3 dimensions. And it's mapping to this Dirac spin space, which is a 3 sphere. And this mapping is characterized by integers, and that's what we computed. Now, it's not hard to put in the actual Wilson propagators and show that exactly at the values of when, so you think that this could never change being a winding number, but the place where it can change is where our n vector is ill-defined, namely when a squared plus b squared equals 0. That's exactly the point where the bulk has a gap, has no gap. The gap closes in the bulk. And that occurs only at m over r equals 0, 2, 4, 6. And so you can put in the Wilson propagator, and you can show that it jumps just the right amount to take into account the change in the number of modes on the edge. And this works also, of course, when you go from 5 to 4. It's a map from a 5 torus to a 5 sphere. These winding numbers are all characterized by integers. When you put in the Wilson fermions, you get the correct integers. So This turns out to be we didn't know at the time, I didn't know anything about condensed matter theory. This turns out to be the equivalent of the calculation that Thallos and collaborators did in 1982 to show why the integer quantum Hall effect was quantized. It's in a completely different language. They're doing Berry's phase, they're computing derivatives of wave functions with respect to momentum, but it's obviously the same physics in the end. So if you want to see what a map from a torus to a sphere looks like, Mathematica has this double mapping, winding number 2 map that allows you to visualize it. So the topology, by the way, was in momentum space. Momentum space is continuous on an infinite lattice. And so that solves that question, how you can have topology lattice. It's not in coordinate space. So if you look at the condensed matter system for the integer quantum Hall effect, they usually plot the resistivity, which has steps in 1 over n, where n's an integer. It's too bad they don't plot it as conductivity, where the steps would be integer. That seems more natural for a theorist. If you plot the conductivity for Wilson fermions, you get this picture here. As a function of m over r. And if you actually put back your units, you find that the units are correct. It's in units of the von Klitzing resistivity, quantum of resistivity, h over e squared. If you look at the phase diagram then for Wilson fermions, it's a little bit more complicated than people had expected. So here I'm plotting the gauge coupling on the vertical axis versus this ratio m over r, the mass of the Wilson coupling on the horizontal axis. Of course, because of asymptotic freedom, you want to tune down to g squared equals 0. In practice, usually stop at where the lattice spacing is about 2 GeV inverse. And so according to the usual Wilson dogma, you have to find a second order phase transition and tune to it, because that's where you get the long correlations that are interpreted as continuum particles that don't know about the lattice. Here, however, what we find is there's a phase in blue I won't talk about, but in the yellow regions here are the topological phases. These are the regions where the entire theory is gapped. Normally, you'd say this is useless for describing continuum physics, but if you look at an edge of the system, you find continuous physics. And because it's a broad region, there's no fine-tuning involved, and radiative corrections aren't going to mess this up unless you have strong coupling. So those are the topological phases. So I want to just say one more thing about this, which is that those yellow phases, of course, are not universal. They are specific. This picture is specific for Wilson fermions. But the message from this is that when you have topology in momentum space, the UV completion of the theory makes a difference and has real effects. So while this is not the phase diagram for QCD, presumably there is some UV completion of QCD that renders the momentum space finite. If that's the case, it probably has topological phases. It's a little tough to slice space-time and see what lives on the edge of it. So I don't know quite how you can tell what phase whether we're in a topological phase or not. But it's completely reasonable to expect that QCD has some phase diagram that is analogous to something like this, even if this is not itself the correct theory of the UV of our world. So you go back to the Callan-Harvey paper and ask, did they know they were talking about the quantum Hall effect? And you look through it and you find one mention, and it says, it is amusing to note that the geometry of this current flow is like that of the Hall effect. Current flows in a direction perpendicular to the applied electric field. It's missing two critical words, integer quantum Hall effect, and this is a big deal because 4 years later, Duncan Haldane wrote the first paper down that showed you could get the integer quantum Hall effect without a magnetic field. This was not known to condensed matter physicists, and it won him the Nobel Prize. All you need, he showed, was time reversal violation, and Callan and Harvey had put in time reversal violation in the form of the mass and the bulk. So there's nothing more terrifying to a theorist, I think, than thinking that you held in your hand a diamond in the rough and cast it aside, assuming it was a common pebble. So these are really good scientists here. So it was interesting to me, sociologic, to ask, how were they able to miss this? And There are a number of reasons. First of all is a sociological one, which is the condensed matter theorists and particle theorists tend to regard each other as aliens. Yeah, you see them poking at a little pile of green slime with great excitement, and you would like to know why they're so excited about it, but then you realize you're going to have to spend years learning alien declensions and conjugations to be able to speak to them, and you say, it doesn't matter. So you miss out. More technical reasons, Kaplan and Harvey were interested in the divergence of the current because they wanted to show that the current coming in had the right divergence to cancel the anomaly on the edge. Because of that, they were looking at something finite. They didn't have to think about a regulator. So they didn't put a regulator in. If you don't put a regulator in, you don't have a compact momentum space and there's no topology. So regulators don't decouple from the Chern-Simons term. So in fact, the number they get for the current is off by half. If I add a Pauli-Villars regulator, I get the red current that I add to the Kaplan-Harvey current. So you get twice what they said from one side and nothing from the other side. That does not change their conclusion about the divergence canceling the anomaly, but it changes their conclusion about what the current should be. If they had computed the resistance, correcting for the factor of 2, which is sort of a strange thing for a particle theorist to compute, if they took the electric field and divided by twice their current, they would have found 1 over 2 pi. And 1 over 2 pi is a nice number, but I mean, there are lots of nice numbers, right? They had rescaled the gauge field by the electric charge so that the covariant derivative was d plus a. It's much nicer to work with that. They had also set h bar to 1. If you put them back, their 1 over 2 pi is h over e squared. So they didn't see the quantum of resistance here. And finally, and this is probably one of the most important things, they had such a simple UV to their theory, no regulator. They didn't have any knobs to turn that would allow them to see the current jump. That was only when we put in the Wilson fermions with the extra term that it surprised us by showing that you could make the current jump like that. So now a little bit more forward-looking. Where is this connection between the integer quantum Hall effect and QCD gone since the early 90s? So in the condensed matter world, in the 2000s, they realized that the integer quantum Hall effect is one of a large bestiary of topological materials in different dimensions. And in 2010, Kitaev put some order on this, showing that they can be classified in this really pretty periodic table. It's the same periodic table you can see if you look up homotopy classes of fundamental groups in Wikipedia. And the classes of different topological materials really just are different classifications of free fermion theories according to whether they have a charge conjugation symmetry, whether the charge conjugation matrix is symmetric or antisymmetric, if there's a time reversal symmetry, and whether or not there's a fermion number symmetry. So the theories with Majorana masses are like the topological superconductors. Ones with Dirac masses are the topological insulators. So the question then is, are there more ways that we can develop connections between quantum field theory and these different classes of topological materials? And is there any way for cross-fertilization? So two things that come to mind is that in the lattice community, people realized that there was some sort of more formal apparatus that you could use for describing domain wall fermions. In particular, there was an equation written down by Ginsburg and Wilson back in '83 before domain wall fermions. They asked, what would a perfect chiral symmetry look like? Namely, within the constraints of the Nielsen-Namiya theorem where chiral symmetry is violated, is it possible to have a theory where only violation of chiral symmetry is due to the anomaly? And so they looked at a block spin average of a theory that had a continuum theory with perfect chiral symmetry, and they concluded that they had this equation here, that the anti-commutator of the fermion operator shouldn't equal 0 as it would in a chirally symmetric theory, but should equal the lattice spacing times d times gamma 5 times d. This is sort of a strange looking equation. It's reassuring that the divergence vanishes as a goes to 0. There's also a way of seeing that, heuristically, why this might be the right thing for the anomaly. If you put the divergence of the axial current at the vertex of a triangle diagram, the divergence of the axial current would be given by the matrix operator, the operator of the anti-commutator of gamma 5 with d sandwiched between psi bar and psi. This operator in the Ginzburg-Wilson equation has a d on each side. Those d's then hit the d inverses of the two propagators on the triangle and tell you that you'll only get something non-zero if all three currents are sitting right on top of each other. So the only way you'll ever see the effect of this divergence is when you're looking at the correlation of three currents at the same point. So it's a short distance effect. Or if you don't have any zero modes in the fermion operator, you can multiply both sides of the equation by d inverse, and you find that the anti-commutator of gamma 5 with the propagator is proportional to a delta function in space-time. So it tells you that the only chiral symmetry violation of the propagator is if you go propagate from a point back to itself, namely short distance physics. So the result was completely ignored for 14 years because they didn't see a solution to their equation. But then in '97, Neuberger took the domain wall fermion theory and integrated out all the bulk modes. It was a pretty amazing calculation, and it came up with a beautiful result in a thing called the overlap operator, and he was able to show that it was a solution, in fact, the only known explicit solution to the Ginzburg-Wilson equation. And then finally, Lucier in '98 showed that any operator that obeyed the Ginzburg-Wilson equation had an exact symmetry on the lattice, exact in the action, which prevented additive master normalization, but violated by the lattice integration measure, and that violation gave you the anomaly. So the whole picture came together, and you could understand how you could have these perfect chiral properties with lattice solutions. So right now, actually, this week, hopefully it'll appear, with some collaborators have shown how the Ginzburg-Wilson equation can be extended to all the different topological classes of fermions. And the hope then is that this Ginzburg-Wilson equation, which does not seem to be known to the condensed matter theorists, can give you a better way of understanding the dynamics of edge states in condensed matter systems. So that's one direction I see possibilities for future progress. Another one has attracted a lot of interest from condensed matter theorists, which is that whether they have the key to understanding how to non-perturbatively regulate a chiral gauge theory. We all know that the way one regulates chiral theories is a little bit awkward. Pauli-Villars doesn't work. Dimensional regularization is strained. I think the way one does it is you assume that gamma 5 anticommutes for D4 and less and commutes for 4 to 4 plus epsilon. As I talked to Collins, he told me that there wasn't any all orders proof that this works. It works a couple loops, people know that. It doesn't seem to be a pressing issue because the weak interactions are weak, so we don't really need non-perturbative simulations of the chiral part of the standard model unless you want to do, say, baryon violation at finite temperature or something like that. So it's not been a pressing issue, but it's still sort of an embarrassment, I think, that we don't have a non-perturbative regulator for the standard model. So there have been many, many approaches, but one that seems to be gaining traction again is originally suggested by Eichten and Preskel. The idea was write down a theory of the standard model with vector-like fermions and then find a way to gap the mirror fermions. Because it's a chiral gauge theory, you can, when you remove those fermions, you cannot give them a mass. You know that requires breaking the weak interactions to give quarks and leptons their mass. But they suggested that interactions could basically make baryons that become gapped. There's nothing to forbid that. But it's a strongly coupled problem, and it's not obvious it works. But it's been recently reinvigorated by the fact that that in condensed matter systems, it's known in a very low dimensional model, namely a wire with 0 to plus 1 dimensional edges, quantum dots for edges, that this can be done. Fitkowski and Kitaev wrote down this model where you had massless Majorana fermions at the end, and they showed by putting in that their masses are protected by time reversal invariance. It's the analog of the gauge symmetry. So you can't put in a mass to gap them, but you can put in 4 fermion operators that can gap them with the curious restriction that you can only gap 8 flavors at a time. That 8 comes from a Tufts anomaly matching condition, which involves a Z8 discrete time reversal anomaly. So a lot of condensed matter physicists got very interested in saying, can we extend this now to 4 dimensions and use this to make a domain wall theory of the standard model, our particles on one wall, the mirror particles on another wall, and then put in interactions to make the mirror fermions heavy. And people have even speculated that the 8 in the Z8 is important, and that we should think that maybe that's why our particles naturally fit into SO10 representations of a spinor with 16 fermions, because 16 is a multiple of 8. That might be just numerics, or it might be something deep, but I don't know. Another approach that I find interesting is a generic one that perhaps you can write a 4D chiral gauge theory, any chiral gauge theory, anomalous or not, as a 5D theory. But then when the anomalies cancel, it can be expressed in terms of a low energy 4-dimensional limit. So this has been given new life also by the enormous amount of mathematical firepower that has been directed at topological materials over the last 10 years. In particular, there's this formula by, that appears in a paper by Witten and Yanakura that the generic partition function for an edge state with a bulk, this is very similar to the Kaplan-Harvey picture, but it has some important differences. You get the square root of the Dirac determinant on the edge. Square root of the Dirac determinant is sort of what a chiral fermion is, but this is the modulus. Does not contain the phase. So this is something we can compute on the lattice, because you can compute a Dirac determinant principle. And then there's the phase, and the phase involves the eta invariant for a 5-dimensional or a bulk Dirac operator, which has self-adjoint boundary conditions, namely not domain wall boundary conditions, but ones where, say, the one they choose is where the fermions on the boundary are in their ground state. It's a little bit obscure, but it's not a domain wall type boundary condition. So the Dirac operator is Hermitian. And this eta invariant is just the sum of the signs of the eigenvalues of this Dirac operator. So we have a formal formula for what the desired phase is for a chiral fermion determinant, and then the question is, could this be something that's computed on the lattice? And then would it have the right property that if you have gauge anomaly cancellation, this collapses to a local 4-dimensional operator built out of the gauge fields. And the reason for thinking that that's likely is that the eta invariant is basically the Chern-Simon term that Kaplan and Harvey computed, and the coefficients all cancel when you have gauge anomaly cancellation. And so this operator would vanish, this 5-dimensional operator would vanish when you had gauge cancellation. But the eta invariant's got more to it, because this isn't quite Kaplan-Harvey. Each of those two pieces is individually gauge invariant, unlike the Kaplan-Harvey picture where you have a gauge variant thing and a compensating gauge variant thing in the bulk. So this is still an open question. So I want to conclude, which is that hidden momentum space topology exists in QCD. It exists in almost any theory of fermions. It's hard to see because it requires the full UV completion of the theory to understand what it is. It connects our relativistic quantum field theories to the theories of topological materials. As a practical matter, it's used routinely now to simulate QCD whenever chiral properties are important and where the fine-tuning savings is worth the extra cost of looking at an extra dimension. It's possible that some of the developments that Lattice QCD has developed and are unknown in the condensed matter world might be of interest to them. And finally, I'm hopeful that this technology could be useful for understanding chiral gauge theories. And just in general, I think it enriches my view of what the phase diagram for QCD in a theory of everything might actually look like. Thank you.
Thanks for the talk, of course. You know, particular point I trying to make it clear. You mentioned about this. I mean, regularization, non-perturbative regularization of chiral theory, gauge chiral theory. But it's my understanding that there is no perturbative regularization which preserves chiral symmetry as well. So before non-perturbative, I mean, if it would be perturbative, then I would be thinking about non-perturbative, right? But perturbative, I'm not aware if...
Well, people do 1 and 2 loop calculations in the standard model.
Only by Clut force, subtracting stuff which break what events. There is no regularization.
Okay, I would.
You see that?
Well, I mean,
but I think that it's related to what you are saying because the absence, even in perturbative regularization in local form, calls for kind of non-local type of regularization, if you like. So you can introduce something, and I could be. So that's why I wonder. You see that it could be a reason why you need to go to this extra dimension because there is no local form in say in 3+1, and once you said that it is say H state, okay, I'm ready to accept it. Then I would ask why I would not have a theory of H state by itself, forgetting about the history how to derive it. If you would have this stuff, I would say that in some way, this non-local form of regulators is kind of, will still be kind of will appear in some form. Okay, but I wonder what you think of that.
Well, so I'm not an expert in this type of calculation, and if you want to claim that this situation is more of a mess than I was claiming, I'm happy to agree.
Say it again.
I don't know much about these types of calculations. I've never done them myself. If you tell me that
it's normal perturbative calculation, and you know that if you introduce a regulator for fermions, you immediately break chiral symmetry. This is not a big deal, right? It doesn't stop you from calculation because you can, add countertones which restore your plot identities. But what I'm talking about, it's a kind of writing a particular regulator local fields, with heavy mass, which would explicitly preserve chiral symmetry in perturbation theory. But I think that could be related to what you are doing.
I see. Interesting.
Oh, maybe. Two things. One, concerning the ultraviolet completion, what about string theory? Is that a possible
That sounds like
framework
a
in
completion.
which you can do what you say? Could be.
Yeah.
Yeah. And the second is, I thought that Lucier had a formulation of to regularize chiral theories.
I'm sorry.
On the that Martin Lucier had a proposal.
So he has,
I don't know how it ended up.
He has a proposal for U1 chiral gauge theory. It's pretty implicit, and it's never been actually formulated on a real computer. And then he has some consistency conditions that he couldn't prove were satisfied for non-abelian theories. So he had suspicions that the theory could work for a non-abelian theory, but he wasn't able to show it. But in terms of a practical implementation of chiral U1 gauge theory, I don't think that his proposal has ever been put to the test.
I want to ask a question. If you say that it's a matter of principle to consider, let's say, 5-dimensional space, and then in order to have our world, which is chiral, standard model is chiral, you see it on the edge of 5-dimensional space, but then, as mentioned by Arkady, you cannot then cut off and throw away the 5th dimension, right? It implicitly has to be present. Doesn't it mean that indeed it's a feature of nature that we live at the edge, but there is the 5th dimension, and it's not in your imagination just to regulate chiral fields, but it's a natural feature of our world. Wouldn't you say that?
No. The reason why is because of the existence of the overlap operator, where Neuberger was able to derive this purely 4-dimensional operator by integrating out the bulk states from the 5-dimensional theory. And this 4-dimensional operator can be simulated on a computer without ever reference to the 5th dimension, and it obeys the Ginzburg-Wilson relations and has all the right properties. So whether or not the fifth dimension, you could imagine a world where we're just given this overlap operator without the extra dimension. It's not very natural, but
Okay, but then at least you are saying, okay, you insist that there is no, in reality, fifth dimension, but our standard model has to be extended to include this operator, which is in a sense non-local, right?
yeah, it's an attractive picture, but it's got problems since we don't have examples of continuum limits for gauge theories in 5 dimensions, for example. Right, because you don't, if you look at a 5-dimensional gauge theory on a lattice, you don't see a second order phase transition you can tune to get light gluons. So I don't know whether I want to swear that the world has to be 5-dimensional. It's suggestive. But there is no picture that hangs together perfectly. If we were 1 + 1 dimensional, I'd say yes, we live in a 2 + 1 dimensional world and we're on the edge. I don't know about 5 dimensions.
Yeah, but as Arkady mentioned, you know, this problem of dealing with the chiral standard model, even at the perturbative level, there is no consistent way to amend a standard model Lagrangian by any local operator in order to which still would preserve the chiral symmetry, right? Gauge chiral symmetry.
I think the problem leads you naturally to consider extra dimensions.
So it should be very kind of indicative of some great omission in our understanding, right?
You should insist that you discovered 5 dimension, fifth dimension.
I'm sorry?
That you discovery of fifth dimension in our world.
I believe many of you have been there before me. I'm sorry, what?
It's a diamond in the rough. Maybe you're holding a diamond in the rough.
Okay, I won't throw it away.
All right, let's thank David again because because we should break for the coffee break.
Another question from Jeff Baldwin.
All right, I've been told, overruled. Jeff Bodwin has a question online. We'll take that one.
I'm sorry. I'm sorry, start again. I was confused.
Could you say again, Jeff?
I don't like that paper. We could talk about it why, but I decided it was too hard to understand how it could have a Minkowski space version. If you're talking about the one that had weird form factors. Yeah, I recommend you email me. We will discuss this. I can tell you things I didn't like about it.
All right, let's thank David again.